So today we're going to carry on talking about Haem Porphyrin and its symmetry and how we can use the symmetry to understand the spectra of this molecule. Right. So Haem Porphyrin again is here, and last time we looked at what the symmetry elements were of Haem Porphyrin, and we could see them all. You know, the rotation axes and the reflection planes and things. And now we're going to start thinking about the vibrations of this molecule. Okay. Now, to do this, what we have to do is we have to first of all create a basis set, right? And we're going to have to look at how that basis set transforms under all of the symmetry operations we found last time, right? So I'll do a different video, I think, on sort of general what basis sets, representations and things are, but hopefully this is familiar to you at least slightly. So, if you can see on my my whiteboard here, what we're trying to find is this thing, gamma 3n. That's the goal of this video, is to find what this is. Now, what does that mean? Well, capital gamma is a symbol for representation, right? So that's the representation of the 3n basis, right? That's what I mean by the 3n basis. Well, a vibration, right, is just, you know, in a molecule is just when atoms in the molecule move around, right? That's what vibrations are, fundamentally, okay? And so to analyse this in a sort of symmetry perspective, what we do is we create a basis set where we put a set of coordinate axes, x, y, and z, because atoms can move in x, y, or z direction. Put that on every single atom, and we see how that behaves under the symmetry operations of the group, and then we and from that we can figure out this representation, and from there we can figure out the spectra of this molecule. Okay, so to help us do that, I've upgraded my placemat from being coins to being an actual drawing of some parts of Haem Porphyrin. So I've left off lots of it, all the dotted lines are just sort of extra structure, and you'll see shortly why I've only drawn on the 4 carbons, 4 nitrogens and the iron in the middle. Okay, so the first thing, an easy thing to do is, we obviously call this 3n, because it's 3 coordinate axes for every atom in the molecule. So how many atoms are there in this part of Haem Porphyrin? Well, we're going to ignore the hydrogens for now, to simplify things, and then we're going to say that n, therefore, is 25. If you don't believe me, you can try to count it yourself, but it's 25. So 3n is therefore 75, okay, and so we know n, we know 3n, and we're also going to have to know in a minute what the point group is, and we did that last time. We can see it's D4H point group. Okay. So just to illustrate what I meant by putting axes on every single part, every atom in the molecule, right? So I've drawn out here, as you can probably see, this central part of Haem Porphyrin, the iron with the nitrogen bounded to it, bonded to it. And then what I'm going to do is, to that, I'm going to take a set of coordinate axes and put them on every single atom. I've only drawn it on the nitrogens here, but on every atom in the molecule. So all the carbons, nitrogens, and on the iron. Now you might think, well, why have you picked this specific X, Y, Z axis? That's a good question. And really it's for convenience, right? So I know that X, Y, and Z have to be orthogonal, so I can't sort of put them all in the same direction or something, but I know I'm going to have, you know, an X, Y, and a Z in some way. And, you know, I could have put them so that the X's are all pointing up and the Z's were pointing a different direction, whatever. But it's convenient for what we're about to, and I'm about to see why it's convenient for us to draw the Y and the X and Z like this. So the Z axis comes out of the plane, out of the screen towards you, and the Y and the X are as they're drawn. Okay? And I've drawn them on this iron here as well. I've drawn the Y and the X like this. Okay, and the Z's coming out towards you. Yep. Okay? And before we just sort of crack on with finding the representation, what we have to do to find the representation is we have to find the character, right? The character of all of these sort of elements of our basis set, or the character of them under every symmetry operation in the group. Okay? So what that means is I've got to look at all these axes. So here I've got my Y and my X axis, and I've got to look at how do they change when I apply a symmetry operation to those axes, right? And there's 3 ways that they can change. So if I have an axis somewhere and I apply a symmetry operation and it doesn't change, that contributes +1 to the character. Okay? If I have an axis somewhere, I do a symmetry operation, and what I do is I kind of invert that axis, so I kind of make it point in the opposite direction, right, to itself. Yeah, as in, like, if I imagine having an axis like this, and I make it do this, right, and it has to be that, not sort of like that, right? It has to be kind of in the same place, but pointing the other direction. Then my character is -1. And otherwise, if the axis goes from being like this to like this, or if it moves, right, in some way, then it contributes 0 to my overall character. And I think it's easier to do this with an example than it is to think about it abstractly. So let's just do an example. So let's think about Haem Porphyrin. So we know it's in D4H point group, and here I've helpfully drawn out for you all of the symmetry elements that we identified last time in Haem Porphyrin. Remember, of course, we have n is 25, and therefore we have 75 axes to think about. Okay, so that probably sounds horrific, right? We've got to think about how 75 different axes change when we do an improper rotation. You know, that sounds like an absolute nightmare. But in reality, it's much easier than this, because we can use the fact that from characters, right? I said that if a character, if an axis is either moved or if it's unchanged, it gives me a +1. If it's reversed, it gives me -1. Anything else, it gives me a 0. So if an axis moves to a different location, then it gives me a 0 to the character, right? So I can ignore it completely. So let's first of all think about, let's go along this table and think about how our 75 axes will behave on each of these elements. So E, the element of doing nothing, right, is very simple, because that every axis is going to be in the same place as it was before the operation was applied. So every axis gives you a +1, so I get +1 75 times, so I get 75 in here. Okay. Then let's think about the C4 axis. Now it gets interesting. So the C4 axis, as we showed last time, comes out of the iron, right, towards you, coming like this, right? And let's think about how that will, how the axes are going to behave. So one really helpful thing is that if I rotate around this iron, right, look at where the atoms go. So looking at the iron atom, if I do this, it doesn't move, right? It rotates, but it doesn't move. Okay. Every other atom will move, right? And therefore, all the axes on every other atom will also move, right? So all the axes on every single atom, apart from that central iron, are going to contribute 0 to our character, because they all move, right? And you know, the axes on this nitrogen, you know, they're moving, and they're not going to be mapped onto -1 of themselves, right? They're going to be reversed, right? So it gives me a 0. So I can, for this element, all I can think about is the axes on this iron atom, and that makes life a lot easier, right? So let's go through X, Y, and Z and see what they give to the character. So if I have the x-axis here, and I rotate it like that, 90 degrees, has that mapped onto itself? No, it hasn't, because it was here, now it's here, so it's not a +1. Is it mapped onto -1 of itself? Has it been reversed? Well, no, it hasn't, because that's the x. If it went mapped to down here, that would be reversing itself, right? Like doing that, kind of doing this, right? Isn't doing that, so it's not -1. It's just moving 90 degrees, so it's 0. So the x gives us a 0 into our character, so does the y, by the same argument. And the z-axis, when I rotate, doesn't move. That gives me a +1. So overall, I get a +1 to my character here. Okay. The C2 axis, very similar idea, right? The C2 axis, the first one is coming out again. Same axis as the C4, it's coincident with the C4 axis. And what I do is I take this thing and I go around once, twice. How has that changed? Well, now we can see that the x that was here has now moved to be pointing this way. So that has been mapped onto -1 of itself, or it has been reversed, right? So that's going to give me a -1 to the character. And the y is the same, another -1, so I have -2 so far. But the z hasn't moved, so the z is going to give us another +1, so overall I get -1, -1, +1, which is -1 overall. Okay, those two are fairly straightforward, right? And now we can just think about the other rotations, which are a little bit more involved. So let's think about the C2 prime axes and C2 double prime axes. So let's think where they were, first of all, right? So the C2 prime axis is the one that kind of goes down these nitrogens like this. And the C2 double prime axis is the one that kind of goes down the carbons like this. It splits the FEN bonds in half. So, and you might be able to see now why I've drawn on only these carbons, right? Because remember that any atom that moves under the symmetry operation doesn't affect our doesn't give us anything to add to the character, right? So if I rotate around this axis like this, every atom except for this N, the iron, and this N will move, and therefore give us no contribution to the character. So all I have to do is think about the axes on this nitrogen, this iron, and this nitrogen. Okay, and if you think about it, they're all going to move in the same way because they're all in the same line, right? So we can use that to our advantage. So let's think about this. So if I do a C2, I go from here to here. Again, low budget. I haven't got a thing on this side of the face map, but you can use your imagination and think what would happen, right? So if I have the z-axes coming out of these atoms, and I go from here to here, the z-axes are now pointing towards me, not towards you, right? So they've been reversed, right? So they've kind of gone from pointing this way to this way. They've been reversed. That's going to give us a -1 for each axis, so it's -3 in total. So we're going to get a -3, okay? And then the y-axes, when I do that rotation, aren't going to change, right? They're not going to change. So that gives us a +3. So far I have a -3 plus a 3, which is a 0. And the x-axis, if it was pointing here, up to this direction, if I do this, I can see, on this side of the placemat, it's now pointing in this direction. Right, hopefully you can understand that and imagine that. So that's been mapped onto, again, it's been reversed or mapped onto -1 of itself, so that gives me a -3. So overall I had a -3 from the z, a +3 from the y, -3 from the x. Overall I'm going to get a -3. Okay. And we can consider that as one axis because both of them are going to give us the same contribution, so we don't have to worry about them being two different axes. That's the same axis. Okay, that's the C prime axis. Let's look at the C double prime axis, which now goes down here. Okay, so hopefully now you can see why I've drawn these carbons on, because again, the only atoms that are going to move when I do this are these two carbons and this iron. So we follow a very similar process to last time, right? We have y and x on every atom, and we see how they change. So let's go through it again. If I have the x's, they will go from pointing up here to doing this. I can see on my side of the board it's pointing this way now. It's sort of done like this. You can imagine that, right? So that has moved. It's not pointing on -1 of itself, right? That's giving us a 0. The y will also give us a 0 because moving from this way to this way is not being reversed, right? That's going to point in a different direction entirely. So, well, it's always a different direction, I suppose. But it's pointing, you know, it's not pointing back along itself. Yeah, that's a 0. Okay, and then what about the z-axis? Well, that was pointing out here, and now it's pointing back towards me, right? That's been reversed. So that is going to be giving us a -1 for each z, -3. Okay. Inversion symmetry is actually quite straightforward because every atom, apart from the iron, will move on inversion, right? So the only thing we have to worry about is the iron, right? If I invert y, that has been inverted, it's been reversed, gives us -1. The x, -1, and the z, what's doing this, now does this, gives us -1, so we get another -3. Okay. The S4 you might think sounds complicated, but actually it's not too bad. I remember always being kind of worried when I saw an S in a question, because I always thought propositions were really difficult and complicated, but really it's not. Just remember what it is. It's a rotation followed by a reflection, right? And in this case it's rotating around here and reflecting in this plane, right, this plane here. Okay? So again, if I do the rotation, the only atom that doesn't move is the iron, right? So I can just look at the iron axes. I move this. Y and x both move, like the C4 case. They give us no contribution. And the Z, now on the rotation it's unchanged, but then followed by the reflection in this plane, it goes from pointing this way to pointing back towards me. So that's been reversed. So I get a -1 only from the Z. Okay. And then we're on to the reflections. The reflections are a little bit more straightforward, I think. So the sigma H plane, if you recall, is in the plane of the molecule, right? And so we can see quite easily that the y and the x's are going to be unchanged on a sigma H reflection, right? That's not going to change at all. So we're going to get +1 for each of these, +1 for each of these. There's 25 of each type of axis, so we're going to get +25, +25, +50. But the z-axes are going to be reflected the other way, right? They're going to go back in, pointing the other direction. So that means they're going to get a -25 from the z's. So overall I get, +25, +25, -25, which gives me +25 overall. Okay, and finally the sigma v and sigma d. So where was the sigma v mirror plane? Well, that was the one along the C2 prime axis. That's along here. Okay. And let's think about reflecting in that. So again, you know, as I keep saying this, but to labour the point, the only atoms that don't move are the nitrogen, the iron, and the nitrogen here. Okay, everything else will move. So, yes, then we can just say, well, we have this y doesn't move on the reflection. That gives us a +3 plus 1 from each one, so it's +3. The z pointing out doesn't move. That gives us +1 from each z, so it's +6. But the x will be reflected back to itself. That gives us -1 for each x. So overall I have +3, +3, -3, +3. And the sigma d, which is this mirror plane down here, right, that's actually going to behave very, very similarly. So if I imagine reflecting the y, that goes over here, x goes over here. So the y has been reflected onto a different axis, right, not onto itself or onto the inverse of itself. So that's giving us a 0. The x gives us a 0 as well. And the z's now, the z-axis pointing out here, if I reflect in that plane, it doesn't change. So I get a +1 from each z-axis, so I get a 3 again. So hopefully you can see how we've systematically gone through and filled in this table. And what we've got now is, this is the gamma 3n representation. Okay, but this representation is going to be what's called reducible, right? We can reduce the representation, and that's the topic of the next video. We're going to reduce this and then look at what we're going to see in the infrared or the Raman spectrum.